First off, any questions before we get started today? Anything goings on? No? So we're going to go into chapter 7 today, and the idea is up to this point, if you notice, basically it's like we started with whole numbers, then we worked with them, then we went and we threw in negative numbers, we started working with those, then we threw in fractions, we started working with those, then we threw in decimals and we started working with those. And so each different chapter we've gone through, we've sort of introduced a different type of number. So in chapter 7, the first thing we're going to talk about is number systems and sort of how all the numbers relate to each other, and then just some properties of working with the real numbers. So so what happens is, so first off, at the very beginning, when we just had like whole numbers, so if you have the numbers like the numbers that you count with, basically, okay. So like first you started off with the counting numbers, and those are just 1, 2, 3, and whatever for on forever, and these were probably the earliest numbers that were ever recorded and written down. And then I mentioned before that, if you look at some of the old number systems, like ancient number systems, they actually didn't have a zero in them. And the reason is because most, there were people that thought, why would you record zero? Because why would you talk about a number that doesn't exist? Okay. So, of course, eventually we did include zero, the concept of zero. So if you throw in zero, that's what we would call the whole numbers. All right. And so those are just like the whole positive values. All right. So once you get beyond the whole numbers, well, then when we started subtracting values, it's like if you have 3 and you take away 7, well, that takes you out of the whole numbers and it takes you into negative territory. So then we throw in the negative numbers, and that gets us the integers. All right. And so the integers, those are the whole numbers, but then throwing in all the positives and negatives. Okay. So you got counting numbers, toss in 0, you get the whole numbers. Toss in the negatives, we call those the integers. All right. Then, what happens is we start getting into division, and then we start creating fractions. Okay. And so when you get into fractions, things like, a half or 2/3 or whatever, so then you start throwing in negative 5/7, right? You get these negative and positive fractions. Well, if you're going to throw in all of those, that's a bigger class than integers, because the integers don't have all the fractions in them. And so if you throw in the fractions, these are called the rational numbers. Okay? And the reason they're called rational numbers is these are numbers which can be written as a fraction. And another name for a fraction is a ratio. Okay, so any number that can be written as a fraction is considered rational. Now, whole numbers are also rational. So like the number 3 is an integer, but it's also a rational number because 3 can be written, right, as 3/1. Okay, so every number. So basically, it's like as the groups get bigger, they still contain every group above it. So the rational numbers have all of the integers inside of them, and the integers have all the whole numbers, and the whole numbers have all the counting numbers. So it's like we're adding stuff in, but we're not taking anything out. Okay. So each group gets like more inclusive. All right. So rational numbers, these can be written as fractions. The thing about rational numbers is if you see them in decimals, they can take on 2 forms. So if you have a decimal that terminates, okay, so that means one that ends, like one that doesn't go on forever, like 0.625, for example, okay, then that would be a rational number. And the reason why is because if it terminates, we know we can turn that decimal into a fraction, because this 5 is in the thousandths place. So we could just rewrite this as 625 over 1,000, right? So if the decimal ends, if it has a terminating decimal or it doesn't go on forever, that would be also rational. And the other ones that you'll see that maybe don't look rational, but they are repeating decimals. So you may have done some calculations in this class where you like plug a division problem in your calculator and it's just like a repeating decimal, like a number just goes on forever. That's actually a rational number. What you see is some numbers just don't translate to tens very well because the decimal system is all base tens, like tenths, hundredths, thousandths. Some numbers don't translate well to tenths, hundredths, and thousandths. So like, for example, like 2/9. If you plug in 2/9 in your calculator, try to turn it into a decimal, what you're going to get is it's just going to be 0.2222222 repeating. Another way to write that, you may have seen like the bar notation, right? Your calculator won't spit it out looking like that. Your calculator will just spit it out with the numbers repeating, but you can write it with a bar over top of it. It just signifies that it repeats. There's a repeating pattern. All right, so what you got here is you've got different classes of numbers, right? And you can kind of I'll draw like a little picture here. So I have a picture on this worksheet I'm going to hand out. But, so the idea was that first we started with these counting numbers, Then someone realized that 0 exists, like you could have 0 in there. And so when you throw in 0, you create a bigger group of numbers, and that's the whole numbers. All right, well then, if you throw in all the negatives, right, so then that creates the integers. Okay. But all the whole numbers are integers. So it's like each one is contained within the next. And then, if you start throwing in fractions that aren't integers, that's how you get what we call the rational numbers. Okay. All right. So they're all just different classes of numbers, and it just gets more general as you go. Now, that almost encompasses every type of number that you probably ever encounter, except for there are some numbers that are none of those things. And we've worked with examples. Can anybody think of a number or an example of a number that we've seen before that might not actually qualify as any of those things? Pi is a great example. Because pi is a number, its decimals go on forever and it never repeats. So it's not rational because it doesn't terminate, and it's not rational because it doesn't have a pattern to it. The decimals go forever. So what we have is we have another class of numbers beyond that, and those are called the irrational numbers. Okay, and the irrational numbers, these are things like pi. The other things that are irrational numbers, these are like square roots that don't have perfect squares. So like we saw, I think on the last test, like you could have like the square root of like 50, for example. Well, 50 doesn't have a square root, so try to plug it in your calculator. What does it do? It just spits out a decimal that goes on forever and never repeats. Okay. So then we have the rational numbers that can be written as fractions or in decimal form. They end or repeat. Then you also have the irrational numbers, and those are these types of numbers that you encounter that don't actually qualify as those. But they're still like whole number values. Like pi we can approximate as 3.14. The square root of 50 is just a little more than 7. Plug in your calculator, you see that. Okay, so they're still they're positive numbers. Like they're not made up. They just don't classify as rationals. So then if you put together the rationals and the irrationals, so you've got, the counting numbers, the whole numbers, the integers, the rationals. Then you tack on the rationals. Then together, this creates what we call the group of all real numbers. Is it weird? It's kind of weird, but it kind of makes sense when you think about it because it's like it evolved. I mean, the number systems that we created just evolved over time, right? It's like, okay, 30,000 years ago, people just needed to count stuff, right? So we had counting numbers. Then someone thought, hey, what happens if you have nothing? Okay, well, we can have a symbol for that. That's 0. Then all of a sudden you start formulating things like addition and subtraction. Well, what happens when you take away more than you start with? Okay, well, now you have to have all these negative numbers. So now you have the integers. Okay, well, then you start thinking about, well, what happens when we start splitting things up? Well, you can split whole things into parts, right? Okay, well, now you have to come up with these new types of numbers that are called, fractions or ratios. So that's how we create the rationals. Well, but then we have other stuff like, how come every circle, when you take the circumference and divide by the diameter, creates this number? Like, it's a real number, it's a value. Or the square root of 50, like, you start to try to take square roots of numbers. Well, some numbers don't have square roots, right? It's just a different type of number. And so they just get more and more general as you start to come across different applications where you're trying to solve problems using numbers. So that together, these create all of what we call the real numbers. So, all right? And then numbers, excuse me, numbers can be classified as multiple different things. So like 3 is a rational number, technically, because you could write it as a fraction. But 3 is also an integer, because it's a whole number. And 3 is also a whole number. And 3 is also a counting number. So numbers can fall into different classes. All right. So these are the number systems. And then if you really want to get goofy, you can actually have non-real numbers, which happens when you try to start. Because if you go to start taking like square roots and negative numbers, those are non-real numbers. That's why when on the test it's like if it's the square root of a negative number, you just write not a real number. It actually is a number. It's just not a real number. So it doesn't classify as any of these things. But anyways. Okay. So far so good? All right, so these are the number systems. So I have some examples on here where you can just try and classify numbers as belonging to the system. I also have a picture for you to use for reference. But that's the definition. Okay, so then there's also properties of real numbers that we can kind of rely on. So you'll pretty much always be working with real numbers. There's really no applications that you're probably going to run into in real life where you would work with like imaginary or non-real numbers. We'll pretty much always work with real numbers. So there are a few properties of real numbers, though, that we can work with. So first off, there's something called the associative property. Associative property. Okay. And what the associative property tells you is it says that, okay, let's say that you have, let's say you're doing like addition, right? And you want to add 3 numbers up together. Does it matter which numbers you add first and which numbers you add second? It doesn't, right? Like, so you could take A plus B first and then add on C, and you would get the exact same answer as A plus B plus C. True? Yeah, that's always going to be true. And it turns out that it also works for multiplication. If you're going to multiply 3 numbers together, does it matter what order you do it in? It doesn't. You could do A times B first and then multiply by C, or you could do B times C first and then multiply by A. It doesn't actually matter what order you do it in. So that's called the associative property, and that works for addition and multiplication. That'll always work. So it says it doesn't matter what order you do it in. All right. The other one that we can take advantage of is something called the commutative property. Okay. So in the commutative property says that you can do it in any order, but you can also write it in any order. So, for example, A plus B is exactly the same as B plus A. True? Same with multiplication. A times B is exactly the same as B times A. All right. So that's the commutative property. It also works for addition and multiplication. By the way, do these work for subtraction and division? They do not. Yeah, because you get into trouble if you start trying to do this with subtraction. So you can't just be flipping things around with subtraction. You have to be careful when you have subtraction and negative terms involved, and division too. Okay, because like for example, we know that 5 minus 3 plus 2, like, is this? Wait a second. Maybe I don't want to. Maybe that's a bad example. Oh shoot! Just got rid of the whole thing. Oh well, sorry. Did you guys get that copy down? I think I can undo it. Yeah. There we go. Excuse me. What am I doing? Don't hit that button again. Like for example, I don't want to use A again. For this one, if you try to do like 3 minus 5 minus 2, is this the same as this? No. It's not, right? And you can see it because on this side, 3 minus 2 would be negative 2 minus 2. But on this side, it would become 3 minus 3. Right? So on the left-hand side, you'd get negative 4, and on the right-hand side, you'd get 0. So it doesn't work for subtraction. Okay? So you have to be careful. It kind of works if you pay attention to signs, though. Because really, the way you want to think about this is, 3 minus 5 minus 2. All right? You could do 3 minus 5 first and get minus 2 minus 2. Or if you were paying attention to signs, right? Well, what's minus 2 minus 5? Well, no, what if that's a negative 5, though? Yeah, see, if you think of this as minus 5 minus 2, then what would that be? It would be minus 7, right? And so negative 2 minus 2 is negative 4, and 3 minus 7 is also negative 4. Okay? So there is a way to think about associativity and commutativity working with subtraction, and specifically, what you have to think about is you have to consider that if you have an expression that has like multiple terms, the sign is attached to the term. That's the key. So like if I have an expression like 3 minus 5 minus 2, then this is a minus 5 term, this is a minus 2 term, and this is a plus 3 term. Okay? And if you attach the sign to if you think of that sign as being attached to the term, then the associative property and the commutative property actually work. Because essentially, you're just moving integers around. So you can do it, and you can move it around in any order you want as long as you take the sign along. So like you could rewrite this as negative 5 plus 3 minus 2. Or you could rewrite this as minus 2 minus 5 plus 3. Right? And so the key is that when you have an expression and you're trying to move terms along, or move them around, the sign goes along with the term. That's the key. And so technically the associative property and the commutative property, the way they're written right there, that would only work for addition and division. But if you think about the sign going along with the term, you actually can move subtraction around. It's just that it's like here, we were starting at 3, we were going back 5, back 2. Now, but that's the same as starting back 5, adding 3, and then going back 2. All of these 3 expressions will get you the same answer as long as you take the sign along for the ride. Okay? Okay, so that's important. That property is important because we'll get into, so far our equations and stuff that we looked at, they weren't usually like multi-step equations, but if you get into multi-step operations, it's really important to take note of that, and I'll show you why. So when you have an expression, it's important that you should always simplify, just like we always simplify fractions, we always simplify expressions, and typically what that means is it means combining like terms. All right, so let's say, for example, I had an expression like 5x minus 3 plus 2x. So it's just an expression. It's not an equation because it doesn't have an equal sign. It's not an equation, so it doesn't like have a solution. But it can be simplified. Why? Yeah, because what we have here is we have a 5x and a 2x term. They're like terms. They're describing the same things. There's 5 of them, and then there's 2 more of them. So what can you do with those is, the commutative property tells you that you can move that 2x next door, and then because they're like terms, you can add them up. And so this expression would simplify to like 7x minus 3. Okay. But it's also important to note that we could have brought the 5x over by the 2x and left the 3 in front as long as we did what? As long as we carried the signs along with it. Okay? So this is what I was saying. It's important to just think of the sign as being attached to the term. Our final answer is going to have a minus 3 in it. Whether the minus 3 comes second or first doesn't actually matter as long as the minus is with the 3. And the 7x is going to be positive. Whether it comes first as a positive x or second as a plus x doesn't matter. They're the same term. It's the same value. Okay? Seem reasonable? What if you have like, let's see, you can have multiple terms, like, so let's say we had like a minus 3x plus 2 plus 5y minus 8x minus 10y plus 8. Okay. So in this case, we have how many different types of terms? We have 3, right? So we have x terms, we have y terms, and we have numbers. So our answer should only have 3 terms in it. So we just need to rearrange these and get our like terms together. So like for example, I have a minus 3x, but I also have a what out there? So there's a minus 3x here, but there's also and it's a minus 8x. So when I combine them, I need to realize they're both negative. Okay. And then we have a 2, but we also have a what? Yeah, a plus 8. And then we have a plus 5y and a minus 10y. So you can rearrange terms as much as you want. Just take the sign with you, and then you can combine them. You don't have to rearrange them to combine them. If you can see how to combine them to begin with, that's totally fine. Okay. So then here we could combine our x terms. So if you have a minus 3 or a minus 3x and you take away 8, where's that going to take you? It takes you more negative. So this would be like negative 11x, right? What about here? If I have a plus 2 plus 8 plus 10, and if I have a plus 5y minus 10y, so I start with 5 and I take away 10, where do I go? Negative 5y. So this would be your answer. Is that the only way you could write that answer? Is there only one single way? No, it's not, because we could rearrange these terms any way we wanted. Like we could put the 10 first, and then put the minus 11x, and then the minus 5y. We could put our x term first, then our y term first, then our 10 term first, right? It doesn't matter which term comes first, second, or last. What's important is that every term has the right sign on it. And typically, if your first term is positive, you don't write the plus on it. That's just like, you could write that as a plus 10, but it's not. We just don't. It'd be like you could write, just like you could write a 1 in front of any number, like an x term is technically like a 1x term, but we don't usually write the 1 there. A positive number is technically a plus term, but we don't write the plus there. We just write the negative if it is a negative term. So, okay. Questions about that? Yeah.
So can it be negative 11x squared or not?
Well, okay, so higher powers are not like terms. That's a good question. So, like, for example, if I had, like, let's say we had 8x squared plus x minus x squared plus 3x plus 5 or something, right? So if you have higher powers of terms, those aren't like terms. Okay. So what you have here is you have 3 terms. You have x squared terms, you have x terms, and then you have numbers. So there's 3 types of terms here, and you can't combine like higher powers of x's with lower powers of x's. You can only combine like powers. The variable, like the term in it, is kind of like the unit. It's like I got 8 of these, and then I also have minus 1 of those. These are the same thing, but those are not the same thing as this, right? And you can see if you plug in a number, like if I plug in 3, 3 is not the same as 3 squared, right? Because 3 squared, if I plug in a 3 here, I'm going to get 3. If I plug in a 3 here, I'm going to get 9. So they're not like terms. So when you go to combine them, I can combine these, right? So if that's an 8x squared, and I'm taking away an x squared, how many x squareds will I have? 7x squareds. Then I have my plus x and my plus 3x. So how many x terms do I have? 4 x's. And then I just have my 5 out there. It doesn't have anything to be combined with. And so this would be the most simplified version of that expression. Couldn't go any further than that. But good question. And the powers, like the powers aren't going to change. So even though there's an x here and an x here, when I combine them, it's not going to become x squared because I'm not multiplying anything. I'm adding and subtracting. So it's just like, this is like, if you have 1 inch and you add 3 inches, you get 4 inches. You don't get 4 inches squared because we're adding and subtracting. If you multiply them together, that's when the powers start changing. So like if you had like an x times 3x, that would be 3x squared because you're multiplying. But if you're adding and subtracting, the powers will not change. So, okay. Seem reasonable? Okay. All right, so I got like this little worksheet here. I got a nice little black and white picture because I don't have a color printer, so you get black and white. But it's colored in the book. But it kind of just outlines the number systems. And then I have some numbers there that I want you to try to classify. Yeah. And then just some working with the properties. And that's all we got for today. So on those number systems, a lot of those numbers